So continuing our discussion with sorting algorithms, we'll see the running time of merge sort. We have already seen the program of merge sort, and if we look this merge sort algorithm quite closely, we will notice that the running time of an array of size n, that means you have an array of size n because everything will be dependent on this only. First, we spend order of 1 time in computing m. What is the m? That is, we are trying to find out the center point or the middle point. So this is only order of 1. Then we make 2 recursive call to merge sort. Merge sort means the sort, we call the sort itself with arrays of size what? This is what? Half, and this is half. So n minus 1 by 2, n minus 1 by 2, and we take floor and seal of both of them. One is floor, one is seal. So half and half we divide. So this was the computation, this is the calling, and the major part is the merge. Actual work is done here. So merge goes through 2 sub arrays, this of one loop, always increasing one of I and j. We always increase by I and j, whichever I and j you choose, but this takes order of n time. For computation, let's take this t, and t is for time, and for this is the trivial symbol or that we take for computation of time. We say this is t for time and for numbers, and to denote this for worst case running time, because we are only interested in worst case running time of any sorting algorithm. So in this case merge sort, and this array is of size n, but we don't know this tn, but we have already seen that the recurrence relationship will be something like this. After discussing all these three, that order of 1 time in computing this m, and we compute it for say n times. So let us at the start we say we have this half time for this half 1, time for this half 1, and then merging of n, this theta n. So half tn by 2, tn minus 1 by 2 for this, tn minus 1 by 2 for this, and t or order of f theta of n for this. And for this n, this will be order of 1 as I suggested. These 2 cases are just the base case whether this recursion relation should stop or bottoms out. And how we are going to find this first relationship? We are working with the array of size n, and n is actually for the time for merge and the computation of this m, the middle point. So for that we take theta n time plus this the time of 2 recursive calls, and we don't know how long these are going to take. So having worked out this recursion relationship, because this is very important, once you know this recursion relationship, then only you can carry out your running time. And this n minus 1 by 2, n minus 1 by 2, by practice we can just replace it by n by 2, it's equivalent, and our relationship will become 2t n by 2. That is, if this is n by 2, we add them to n by 2. So this is a type of recursion of a dot t n by b plus fn. This is very frequent in divide and conquer algorithm. This is the general form. These are a and b are constant. See, 2 and 2 are constant here. These are a and b, and with some function say f, and this is our function f, right? And we will be solving this with a recursion tree, and you'll be able to know how we can actually get down to the order of n log n. So this is our n. This was total n. This n is nothing but this is a recursion tree of merge sort, and this number in the boxes are the array sizes. And we also know that the work for this merge for an array of size s is theta s. N for n, it is theta n. This is what we know that merge is going to take. Merging will take order of n time for n values. We divide this, or divide and conquer, we apply the first one, we divide it to n by 2 and we divide n by 4 till the time the last member remains. So what we are doing is, we are dividing theta n, we are making n by 2, so the time will be 2 into theta n by 2. Then again 4 into theta n by 4. That will again be theta n, because this is going to remain for n. It, as I said, that it has to be theta n. And at this point, it will be 2 to the power k theta n divided by 2 to the power a theta n. This is actually general form. But we are starting from this n by 2 and reaching till 1. So n theta 1 theta n. So every time it will be theta n only. So there will be no change. We are just trying to replicate and form the recurrence solution. As we have seen that this is the general form. Hope you understood this. N by 2, n by 4, and n by 2 to the power 8 k. This 2 square 2 to the power k. So this is how we achieve this 2 to the power k theta n to the power n by 2 to the power k, which is actually theta. But here we understand that when we are dealing with this 2 to the power k value, the number of levels will become log n. In this, these are the number of levels, and this will only become log n. Technically, it should be log n this of sleeving of this. The total work of summing up, because we have n numbers, we already know this n, and there are log n levels, so it will be n log n. And we'll just because every level, all algorithm will sum up to constant factors, so we say it to be order of n log n. And finally, our relationship will become like 2t n by 2 plus n, and this will result, as discussed here, it will be only theta n log n. So this is how we achieve the relationship of running time Tn to be theta n log n. But there is one plus also. If we see that one plus is also coming, there is a separate discussion for this, and for just by putting this k equal to n minus 1, we will be getting rid of that 1. And don't worry about that, because n into n plus n log n will always be n log n. N log n is somewhat greater than this n. So this was the basic idea about merge sort, how we achieve n log n in merge sort. Thank you.